Hello everyone, welcome back to another study shed video. Today we'll be going over the topic of solving differential equations using series. So first off, why would we use a series to solve a differential equation? So notice how when we have integrals such as sine x over x dx, functions such as these are very hard to integrate directly. However, if we write sine x over x as a Taylor series, a function is very easy to integrate because polynomials are trivial to integrate. Similarly, we apply the same method for solving differential equations, especially ones with non-constant coefficients. As you can see here, one of the coefficients in this differential equation is an x, which is not a constant. And so we'll employ series to use such a to try and determine a solution. So how would we start? Well, the easiest way to start is we can start by, let's center our series at 0 to be a Maclaurin series. However, note you can't do this all the time, as it depends on what the coefficient for the y double or the highest order derivative is. As if this was an x as well, we won't be allowed to use it. The general rule for finding where you can center your series is you look at the coefficient in front of the highest order derivative, and you notice whether where it equals 0. If it equals 0 at a certain point, you cannot start your series at that center. So in this case, since it's 1 is never 0 anywhere, and so we can center our series at 0. So our solution will be in the form the sum from 0 to infinity a of n x to the n. So it's y double prime, so we'll have to differentiate this twice. So the second derivative of our y here is the sum from 2 to infinity a of n, not a of n, n times n minus 1 times a of n times x to the n minus 2. Notice we get this, if we differentiate this once, we'll get n times a of n times x to the n minus 1, which means we'll have to start this index at 1. And if we differentiate that again, we'll get the sum from 2 to infinity, because we're going to decrease this value one more, and we're going to get n times n minus 1 times a of n times x to the n minus 2. So now we have our second series, which is just a direct plug-in of this equation, and we get minus x times this series, which is the sum from 0 to infinity a of n times x to the n. And now to make things easier, we're going to multiply this x into our series. So this just becomes n plus 1. So here, and this all equals 0. In fact, let's just rewrite this so we have space to write all in one line. So we have minus the sum from n equals 0 to infinity a of n times x to the n plus 1, which comes from multiplying this series by x. So 1, and this equals 0. So what will we do from here? Our first goal is to try and combine these series, and the way we can do that is we need to have two conditions met. First, the lower indices need to match, and second, the degree of x also needs to match. So the first thing we're going to do is we're going to try and match the degree of x. We're going to need to somehow try and transform this x to the n plus 1 into x to the n minus 2. So how would we do that? Well, using our transformation of series, what we can do is, if we subtract 3 from this, we can subtract 3 from the n plus 1. We can make n minus 2 plus 1. We can subtract 3 to get n minus 2. And if we do that, we'll need to add 3 to the lower index to keep the series equal. In addition, we'll also need to subtract 3 from this from this term as well, a of n, as we want the first term to be a of 0. And so if we transform the series, we're going to get the lower index of 3. We're going to get n minus 2. And we're going to get a of n minus 3. And notice now we have these two matching. So we did the first of two things we need to combine series. We got our exponent of x to match. Now we need to somehow try and match the lower indices. Well, in this case, it's really easy. If we just take out the first term and then write the series from 3 to infinity, the two series will match. So what is the second? If we plug in 2 into this series, we're going to get 2 times 1 times a of 2 times x to the 0, which is just 1, plus the sum from 3 to infinity, as this is just a of 2, of n minus 1, a of n, x to the n minus 2, minus this series over here. So let's rewrite that real quickly. Sum from n equals 3 to infinity, a of n minus 3, x to the n minus 2. And notice now we meet both of our conditions. Our lower indices match and our exponent degrees match. So now these series are ready to be combined. Alright, so our differential equation was 2, let's rewrite that, 2 times a of 2 plus the sum from n equals 3. And notice when I will be writing series, I'll just put this, implies that it's to infinity. N equals 3 to infinity of n minus 1, a of n, x to the n minus 2, minus the sum from 3 to infinity, a of n minus 3, x to the n minus 2. This is an x. Right? So now, since the series have the same lower index, we can combine them to get 2 of a. This equals 0, by the way. So we can combine them now. So we have our first term, 2a of 2, 2a sub 2, plus, now our combined series is the sum from n equals 3 to infinity of, so now we're going to combine these two to get, just open our bracket, to get n minus 1, a of n, minus a of n minus 3, x to the n plus 2, n minus 2. Let's put all of these in brackets. We'll change the color to black. And this all adds up to 0. So notice what we did here. We basically, since these two have the same starting index, we basically combine them into one series. Then we factor out an x to the n minus 2. So now we have to notice something. If this series is to add to 0, one thing we know for sure is that this term over here has to be 0, as all the terms have to be 0 for the sum to add up to 0, as x is can be any integer, and if we want it to add to 0, we need every term to be 0. Next thing we need is for this to be 0, as this is the coefficient of x. And if x is anything, we'll need this term over here in blue box to be 0, so that when we multiply that by any number, it will still be 0. So we know two things, that 2a of 2 should equal 0, and that this box should also equal 0. And using this, we can solve for the coefficients. Alright, so we know two things now. We know 2a of 2 is equal to 0. We know n minus 1, a of n, minus a of n, minus a of n minus 3 is equal to 0. So this one is really easy to solve. We can immediately determine that a of 2 is equal to 0. Or not, yeah, 2a of 2 is equal to 0. Now what about this thing? So let's write n minus 1, a of n. We're going to subtract the n minus 3 over to the other side is equal to a of n minus 3. Then we're going to divide this over to get e of n let's move this over. A of n is equal to a of n minus 3 over n and minus 1. This thing over here is what we call a recurrence relation, as we're defining one term of the sequence in terms of previous terms. And what we do over here now is just start plugging in n. So notice our series started at n equals 3. So if we let n equal 3, we get a of 3 is equal to a of 0 over 3 times 2. So let a of 4 is equal to a of 1 over 4 times 3. A of 5 is equal to a of 2 over 5 times 4. But we already know that a of 2 is equal to 0, so we know a of 5 is also equal to 0. If you knew that a of 3 is equal to a of 0 over 3 times 2, and a of 4 is equal to a of 1 over 4 times 3. And we know a of 5 is equal to 0. So you can get a of 6 is equal to a of 3 based on recurrence relation over 6 times 5. But we know a of 3 is equal to a of 0 over 3 times 2. So we know a of 6 is equal to a of 0 over 6 times 5 times 3 times 2. And similarly for a of 7, we can determine this as a of 4 over 7 times 6, which is equal to a of 1 over 7 times 6 times 4 times 3. And we know that a of 8 is equal to a of 5 over 8 times 7, but a of 5 is 0, so a of 8 is 0. So you know that if n equals 2, 5, 8, or anything like that, you know a of n is equal to 0. So that's something we need to know. And over here, using these terms, we can determine a pattern. We'll know that if this n here is divisible by 3, you'll have an a of 0. And if this n here, when it's divided by 3, leaves a remainder of 1, we'll use a of 1. So using this, we can set up our recurrence relation. So we're going to write these terms out really quickly. We're going to get a of 6 is equal to a of 0 over 6 times 5 times 3 times 2. And you get a of 7 is equal to a of 1 over 7 times 6 times 4 times 3. So you'd say a of 3k, or 3n, is equal to a of 0 plus 2, or over 2 times 3 times 5 times 6, dot dot dot, and the pattern we notice here is that, I'll just write dot 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 after this. The pattern we notice here is we have 2, 3, 5, 6, and so on and so on. So if n, in this case, n were equal to 2. So we have 2, 3, 5, 6. So in this case, this is 3 times 2, and this is 3 times 2 minus 1. So the pattern keeps on going on and on until 3 of n minus 1 times 3 of n. And similarly, if we have a of 3n plus 1, instead we have a of 1 over 3 times 4 times 6 times 7. Remember, we plug in 2 here to get 3 of n times 3 of n plus 1. So these are our two recurrence relations. And using that, we can solve our differential equation. Alright, so we have a recurrence relation. And now it's time to multiply it by our polynomial. So we have a of 0, our series we wrote as y is equal to a of n times x to the n from 0 to infinity. So we can write that as y equal to a of 0 plus a of 1x. We don't know what these two are. Plus a of 2x squared and x squared, and so on. We know this is 0, so we can just leave it aside. So we know every 3n term is going to follow the following pattern. So we can say that for every term of 3n, we can write it as this series from n equals 1 to infinity, as the pattern isn't satisfied with 0, and I'll show you later why 0 doesn't work. X to the 3n, so you need a of 0 first. A of 0, x to the 3n over 2, 3, dot dot dot, 3n minus 1, 3n. Right? So that's for every term that follows the recurrent solution for 3n. So we have 3n, n equals 3, 6, a equals a of 3, a of 6, a of 9, and so on. And similarly for the other one that we found, this one from 1 to infinity, of a of 1, 1, x to the 3n plus 1 over 3 times 4 times all the way dot 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 times 3 of n times 3 of n plus 1. Right? So these will give you every term aside from a of 0 and a of 1 plus x. So all we need to do is add those two terms. And so our final solution to the original differential equation, y double prime minus x times y equals 0, is a of 0 plus a of 1 times x plus our two series, n equals 1 to infinity. Let's make this a better equal sign. N equals 1 to infinity, a of 0, x to the 3n over 2, 3, dot dot dot, all the way to 3n minus 1, 3n, plus the sum, n equals 1 to infinity, a of 1, x to the 3n plus 1, over 3, 4, dot dot dot, all the way to 3 of n is 3 of n plus 1. And from looking at the series, you should tell why 0 won't work, as it'll make the denominator 0. And this y over here is our solution to the differential equation, y double prime minus xy equals 0. You plug in y, and you differentiate, you'll be able to solve this differential equation. And that is solving differential equations using the method of power series. Hopefully you learned something new today. And as always, happy studying.